All right. Hi guys.
Hello, mic check, mic check. Hello. Yeah, great. I think this is better. Yeah, I hopefully this is much better. So, before moving on to the second part of this video, let me just quickly go through and rewrap my head around because first thing first, the free access is over now, guys. The website which I was studying. So Pajama Bro, if you are listening to this audio or looking at this video, if possible, I'd love a free access again of the content that you posted. And definitely, it was just, you know, cherry's top, or it was just like top of the cake, cherry. I don't know, whatever the phrase you want to put it or not. Never mind. So, whatever we have studied up till now, let me just quickly sum up to you. First, we understood about ARM Cortex M101, which was the introduction, and wherein we discussed about the ARM CPU architecture. ARM only makes the architecture. The manufacturer CPUs or send RTL to fab. They do not do that. NXP, STM, or Texas Instrument, they are the producers. So this is what the whole thing was. And then later on, ARM itself, if you were to, understand the different categories of the processors they deal into, and is within its name itself. So basically, ARM A, which is application grade processor, which can easily run your Linux, Mac OS, Windows, or any operating systems, sort of like that. So they develop those kind of application grade processors architecture. And then we have our R processor, which is a real-time grade. Basically, anything that needs deterministic latency is a real-time grade ARM processor. It could be your engine control, it could be in your ECU, or maybe something that needs quick operations like airbags opening or something like that. And then the third one that comes in is the ARM M processors, which is basically microcontroller application. So it could be within your toaster or maybe in the windows of a car. So that's what the whole thing is. And then what I studied next was a difference between architecture and architecture. So the main difference between the architecture and the microarchitecture is architecture is your specification, what the CPU should do. All right. So every time you're just reading out this thing, you just quickly grab onto yeah, for beginners. Um, for beginners. I know my typing is a bit slow. Never mind for me that. For beginners, la 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 la. I mean, I'll have to Google it. I definitely don't want to open up my search history because lately I've been jumping around from tasks to tasks, from different tasks. Okay, so yes, it is not showing over here. Never mind. We'll do one thing. How to history? Okay, maybe I'll have to jump to my history. Arm, yes. Arm got his programmers. Yes, this is the one. Great, sounds good, right? Yeah. So these are the different processors, which is ARM, and with the name justified, that comes from. By the way, ARM. The full form of ARM is Advanced Risk Machine, or maybe something like that. I read somewhere, and wait, maybe if it's given away or not. No, it's not. Never mind. So these are the sort of different processors they deal in with. So every time you're reading, maybe wait, okay, yeah. So this is what I was talking about. So this is the architecture. Uh, Architecture is basically the specification of what the CPU should do, right? So every time you're just reading about ARM v6, v7, M, and everything about it. So this is how the architecture is written, like v6, v7, v8. V6 is basically M0, M0 plus, or M1 processors. V7 is M3, M4, M7 processors. V8 is like anything above that, right? So that's how you define the architecture. And about the market micro architecture, it is the implementation of that particular architecture. All right. So the implementation is denoted in this way, like the Cortex series of like M1, M0, M0 plus, M01. This is the micro architecture, which is the implementation of the specification of that particular architecture, right? It could be a MV6, MV7, or V8. So that's what the whole, thing is about. So the next, what we're going to quickly recap about is the mental model of CPU memory interaction. So we know what CPU does and how it operates, right? So it is based on RISC architecture, which is reduced instruction set architecture, and which says that it works on load and store model. So load and store model is basically that CPU has particular registers in it, and what it is going to do is, in order to process some sort of information, it is going to load the instructions from the storage registers, and then store it within and fetch it from the storage and store it in its register files, and then it's going to do the compute, and then after the result it is again going to store that result in the storage. So this is the whole thing, and this is the overall idea of how this mental model of CPU memory architecture interaction actually works. So yeah. Okay, so now coming on to the next part of it is how to master CPU and different models to learn. What are the different models that you need to learn in order to understand about the CPU architecture? So basically, ARM has this load and store model, which we studied like risk based. So it has instruction bus, data bus, and then you have your read write, right? And based on that, we have like basically four models, which is first your programmer's model, and then we have your exception model, and then third one is your memory model, and fourth it could be your debug model. So each of the model is important and very plays a very crucial and individual role in how things work with ARM, basically. So the programmer's model details about the registers within the CPU. So if I were to give you a gist, so these are the CPUs, the band. That's what it talks about. While the memory model features how CPU interacts with memory. It could be a speeding up memory, maybe storing answers in queue. So something like this. Yeah, that every time these are each bit is a D flip flop, and when you make a bunch of these bits or maybe D flip flops, it creates your, hold on, yeah, these each bit is a, you know wait, I'll just get a little bit deeper into it. Load store modeling, la 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 la. Yeah, I think this is it. Give me a second. Yes, this is it. So each bit is a D flip-flop, and when you make a bunch of these D flip-flops, so what happens is you get a register, and bunch of these registers. make your register file, something like this, which has its own clock, write enable, data bus connected, address bus connected, and data out, right? So this is how the memory architecture works, all in all. On the other hand, the debug model, which is serial wire or JTAG, I think JTAG is Joint Task Action Group. JTAG full form, da la 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 la. JTAG, yeah. Joint Test Action Group is an industry standard for verifying designs and testing printed PCBs. So they have their own like JTAG pins and other stuff. Uh, Wait, I'm not sure if it's given over here. La, la, la. Let's just move a little down, move a little down. No, 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 no. No, I don't think so. It's given up. So I do definitely have certain questions for myself, which is I've forgotten about the von Neumann architecture versus Harvard architecture. So I'll just quickly recap for myself. Harvard versus von Neumann. Yeah. As far as I remember, before I click onto that, I think the Harvard architecture has parallel processing in the sense that it could read and write at the same time, and basically it has, you know, the data line and the address line is not same. Address bus and the data bus is different. So it could like call upon that address and call upon that data parallelly. That's why it's much more faster. And while the von Neumann architecture is based on the single bus, so it is sharing both the data and the address bus on the same line. So data bus constitutes of its own address of the data and along with that a data bus. So it has two bus in it, and then the same goes for the address bus as well, which only takes upon the instructions and everything. And then it is also connected with the write or read, active low sort of thing, bus like. So yeah, let's see. Yeah. Um, yes. So this is what I was talking about. So basically, it has its own instruction address and then instruction bus, and then we have our data address, and then it's our data. So, and over here we only have our one address and one data or instruction. So either a data could be fetched or an instruction could be fetched at one time. So Harvard, okay, one human architecture is a digital computer. So John von Neumann in 1945. So the advantage of one Neumann architecture is that the fact all the data instructions are stored in a single memory space helps the process of designing a computer system as there is no need to create a complicated systems of routing since pathways may coincide. Cost effective, a smaller number of components is needed as compared to the other architectural designs, hence more economical. Great. Flexibility is program can always be changed or altered without experiencing a change in some underlying aspects, such as circuitry. Bottleneck issue is shared bus. No, 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 no. Okay, slow. Memory corruptions? No, 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 no. सेम मेमोरी में लाई करते हैं तो टेम्पटेशन ये है कि उड़ सकती है. Okay, sorry for the joke and stuff, but it makes it fun. Harvard architecture is a digital computer architecture whose design is based on the concept where there are separate storage and separate buses for instruction and data. It was basically developed to overcome the bottleneck of one human architecture. Separate memory spaces, fixed instruction length, parallel instruction and data access. Advantage of RODN, faster processing, improved security, efficient use of resources. Okay. Complexity, complex है, the design integrate है थोड़ा, cost ज़्यादा हो जाएगी, flexibility कम है competitors के साथ, अलग अलग memory regions है क्योंकि, yeah, sounds good. Okay, now coming back to what we were studying. All right, तो basically ये है एक, तो अभी ये एक ये चीज पढ़ना है, नेस्टेड वेक्टर इंटरकनेक्ट इंटरप्ट कंट्रोलर. यस, nested vectored interrupt controller. I need to study it like more thoroughly, and yeah, that's something that needs to be learned. But coming on to the programmer's model for now, just give me a few seconds. See, yes, this is the complete programmer's model. We have all in all like 16 registers, and I don't know if it's visible or not. Let me zoom into it a little bit. Yes, I think it's much better now. Yeah, okay, yeah, sounds good. Looks good, maybe. Okay, wait, let me just check onto it once if the mic is picking up noise or not. Hello, 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 hello. Oh, okay, wait. Hello. Yeah, so I think it's good. Yeah, great. Sounds good. Anyways, so coming on to it, we have 16 registers over there. R13, you can see MSP and PSP, which is main stack pointer and process stack pointer. So basically, the in the coming part, I'll explain you why do we have multiple like PSP and why do R13 behaves in two different modes. So in the R14 we have our link register, which is basically every time you're running any function such as foo, bar2. So as soon as those functions end, the code or the instruction does not basically the processor do not forget where it was and where it has to return. This is where it is used to store, right? And the program counter, on the other hand, is pointing to the address where the instructions needs to be fetched from. All right. So, and then we have our five different registers, basically XPSR, which is a program status register. Program status register has it like basically constitutes of three more different registers, which is EPSR, APSR, IPSR. All right. And then we have our pre-mask, fault mask, base pre, which is basically an interrupt mask register. The controlled register, we have, you know, ouch, we have various methods of operation, which we will study, which is a privileged thread plus MSP and PSP. All right. So coming on to another part, what we are going to study is yes. So the control register. Basically, this is the control register. And yes, you can over here understand clearly why we have MSP and PSP. This is the line where the PSP and MSP is the section one. And then we have a privileged thread. I might not be sounding very confident in these topics right now because clearly I myself is also I'm also like trying to revamp on things because this was the first time I studied it and then I took a break. I took a break for like 2 days and I could barely like sit with it. Earlier, it was very fine. Maybe the day I studied it was 100%, and then it started depreciating at a rate of 25% per day. So you can totally understand at what rate I might be today at 5 a.m. in the morning because oh, okay, honestly speaking, this conversation is going a little off topic, but I'm just going to take like 1 minute of your time discussing something. So yeah, I slept at 12, woke up at 3. I don't know why. Maybe something is wrong. But yes, after that I was bed rotting and doom scrolling, basically looking for a different place to live. And when I checked out online, the rent was over the head. Bro, who is actually paying? Well, I don't know. The inflation rate is so high, everything is falling apart. The war is going on. As fucking, honestly speaking, don't fucking care about all those things. Because later on in the future, if right now you are able to focus on yourself and your growth and what you're studying for, and if you are able to achieve that, all those things would be a thing of the past, right? And that's what you want. So pick up your ass, do what you want, and just do it. And the whole point of me making this video or going live and studying is just not for the sake of views. It's just for the sake of me actually picking up my ass, showing up, and doing my shit. And I am not a person who would disrespect his words even a single bit. It's a lie, it's a white lie on my face. My brain is contemplating that and saying me a hypocrite right now when I'm saying this. But I want to affirm this to me, myself, maybe for the future myself, but never mind. Sorry guys, took your 2 minutes, but let's get back onto the topic. Okay, so what I remember from the last time that I studied was I forgot about the link register. Link register, not link. Sorry. The Hindi guys would understand what I mean. Never mind. So the link register, forgot I thought it was status register, which it wasn't. So yeah, never mind. Yeah, okay. So these are the different threads, and we'll come on to this part later on. Let me just quickly sum up with the generalist part. So general registers, we have 16 general registers, and these are the core registers which basically you don't want to fuck around with. And then you basically have these 12 registers, or maybe 12 registers, I'd say, to fuck around with. And these are basically the core registers wherein the instructions are stored. And you don't want to fuck around with these registers because if you do, your system's going to crash. And you do definitely get some sort of privilege and unprivilege. So basically, it is like you'll get the opportunity to fuck around with these registers as well because yes, you can use them as well. But if you're a beginner and basically you need to understand how serious this thing is because it can break your sleep processor. So yeah, and then we have program status registers, which keeps on which basically keeps a track of what's going around and how it's operating, right? So okay, So we'll understand that it has three different parts to it, which is APSR and then EPSR and then IPSR. So basically, it keeps a track of the interrupts that are going to happen and then the conditional statements and what value it's going on. So if we were going to zoom in and zoom out, I think the control register part is much clearer now. Even if it's not, we'll come back to it later on. Right? So in this part, okay, let me just, for you guys only, specifically for you guys, what we are going to do is we're going to do on Figma and we're going to take a screenshot of this whole thing. So, G's learning speed. Yeah, I'm going to explain you in more thoroughly what's going on. Okay, yeah. So we have our colored. We'll take the green first, right? So with these are the different bits. It's a 32-bit series, so like 32, right? So these are the microarchitectures, and then we have written over here the architectures about it, and these are the values which is there, like which keep the status of everything. So yeah, so here in n is the negative number, and 0 is the z, and c is the carry bit. V and q I'm not really sure of, but maybe I've forgotten it. So all in all, if you were to understand, so these NZVQ are a part of what do you say APSR, right? And if you guys are wondering how come I'm so good at Figma, yes, I used to do UI UX as well. Okay, never mind. So and then we have our 26, 24 bit this and this, which is basically a conditional statement. So it I'll just write it down as well for you. N is negative, Z is 0, C is carry, and I don't know what's V and Q. So yeah, so about this one we have like this is our EPSR, which is basically a conditional statements like if else checks if it has any sort of conditional statements like if else, yes, if else, hello, wait, hello, yeah, I, so if it checks, yeah, I think this position is good, right? Sounds sounds so dumb. Anyways, conditional statements, if else or anything, some sort of like that. And then we have our exceptions for interrupt. So it controls the IPSR. Yeah. These are the IPSR, IPSR. Alright. So these are for the interrupts. Interrupts. Mhm. So this was the whole thing. So coming back onto our this thing, right? So maybe definitely like you can go and search for this as well, and you get a gist of what I'm trying to tell over here. Okay? Yeah. So the next thing that we're going to go and try to understand is about the floating point, which is an optional thing. So it basically has like 32 floating points, and this is the architecture. So yes, there's not much to it, and there is the floating point status control register, and yeah, honestly speaking, there's not so much to understand about it. But the CPU definitely has a lot to understand over here. So give me a second. I'll just open up that tab again. Try to make you understand how this thing is working. Oh. I definitely feeling asleep now. Okay, so this is your CPU, right? And okay, just give me a second. Yes, CPU, and this is your registers. All right, and we have understood that this is how it operates. Right. But now that if we were to, understand it more thoroughly, so this whole thing is divided in like two parts, wherein you have your mm, thread and okay, let me just screenshot this as well. Yeah. So these are the two operating modes of the CPU, which is a thread mode, and then we have a handler handler mode. Okay. So and then we have over here that the privileged thing, and then we have a non-privileged, and then a privileged thing. These are the two different modes in which it can basically operate. So the thread mode does mostly the computation part, does mostly the computation, like arithmetic computation. It could be plus, it could be minus, it could be, multiplication, or maybe like division. And then maybe an interrupt occurs, then moves to. This one, the interrupt occurs. Moves to handler. All right. So this is basically how this thing is operating. And if we were to simplify this, and if you find this more, you know, difficult to understand, this is a much simpler model to understand it in this way. So herein you can try to understand that how this thing is operating. So every time your computer starts or resets itself, or your processor starts or resets, it enters into the privileged thread mode, and then overall, if so, this is basically R13 is MSP stack pointer, and it is stack is basically like think of it like this. Like this is your stack, and if let's assume this is your MSP, and this is your PSP, PlayStation, not PS5, PSP, and this is your MSP. Yeah. So every time it enters, it basically like start from here, and then this is your PSP, which is in the say register of a different mode. So which is a privileged and unprivileged mode in order to try to understand that, oh, you want to access certain things of that particular, these registers over here. Like you want to access these and you want to write code onto these registers as well. So this is how you understand about it. So yes, so this starts off within the privileged thread, which is your MSP, and then you program of control register, you write about it, and then you enter into that unprivileged state. So there's no coming back directly from unprivileged to thread. So what you need to do is you'll make an exception or maybe an interruption. You'll enter into privileged handler mode, and then you can just exception exit, and then you'll again come back to the privileged thread. All right. So how it operates is that as soon as you uh, so it comes onto the PSP stack pointer, and then privileged handler come back to the MSP hand. So since the size of the MSP is much larger, so it can basically accommodate all the three of it, uh, or the two of it, in the sense privileged thread and privileged handler. So yeah. So every time like you're moving, it's maybe it starts from somewhere here, and this is your privileged thread. First one is your privileged thread, and then your second one is your unprivileged thread, and then your third one is basically the privileged handle. So it starts off from here and then moves on to the PSP mode and then come back to the MSP. That's what was for the programmer's model. And yeah, I mean, I basically have studied up till this much only. Later on, I was about to study about the CPU model, and so that this topic could finish. Right? And so, what we're going to do today is maybe we are going to try to understand about this CPU model. But since like this, hold on, let me just check how long is this video going. 42 minutes. Okay. So the video is already like 42 minutes. Okay. Why didn't the stream start? Huh? Why is it showing this thing? Oh, understood. Okay. I need to fix the quality of my mic as well. So what we are going to do next is, since we have already completed the revision on this thing, and okay, wait, let's just do one thing. Let's again come back. Oh. Hmm. So we have clearly understood up till now how all these things operate and work. Let me come back onto this storage model because this is something I wanted to come back to. So ways to store a bit, we have our feedback loop interconnected with not gate, and this is a volatile thing. So every time like the electricity goes out, so it come back. So it constantly needs an electricity. So you can think of it like your some sort of volatile memory, right? And then we have our charge tapping, basically a capacitor. Think of it like a capacitor that holds on to charge and you can just read or like store like that. So it is used basically in your flash or EPROMs. And yeah, that's it. Oh, okay. So we are going to study now about the CPU model, right? So, back in 1970s, those who programmed the computers pretty much knew everything about how it worked. Computers were fancy calculators that I think that would be were, grammatical error, never mind. So, fancy calculators that enable people to do more and more. Present time, computer systems are too complex but build on the same basic principles. We'll assume we are still in the 1970s, but the access to popular CPU architectures of today, like ARM and RISC-V. The CPU architecture is not that important, honestly, but using any of these will set the right tone for discussion. Everything learned about these architectures or CPUs will be readily useful in real life. Whatever is stated here should also apply to any other CPUs with minor changes that can't be figured from the CPU datasheet manual. We'll think of the CPU as a simple machine and ignore a lot of details about its implementation. We'll leave out how exactly it works at the hardware level and focus only on the model that represents its functionality accurately. Okay, sounds good. This makes reasoning about C programming very easy, and one can be very sure of what the CPU will do given the instruction sequence. This becomes important when we are trying to understand how the CPU can do procedure calls and jump between different sequences. Understanding this will also open doors to reasoning about how a single CPU can switch between different processes and give the illusion of more than one process running in parallel. Abstraction, ignoring the detail. To give you more, the abstraction of a car, what do we use, is a simplified representation of how we perceive and understand the corresponding dismantle. Understand every intricate detail of its mechanics. We perceive the car as a single entity with various inputs and output mechanism, understanding that by manipulating specific controls such as okay. So we we are basically not going in detail. That's what the author wants to tell. Uh, okay, we are not going in detail of the mechanics of the car, and this is just a representation of the understanding to understand about CPU without going. Hmm. Oh, oh. Hmm. Okay. Controls such as the steering wheels, pedals, and gear lever, we can influence the car's behavior, make it perform certain actions. Steering wheel is a primary control for changing the car direction, speed control achieved during la 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 la. We recognize that pressing la 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 la. A car, of course, is infinitely complex in its implementation, has million moving parts, but we all manage to drive it by having to know it's very little about the internal mechanics. As long as these few abstractions or rules work reliably, no one cares about that. In case of deviation in this model, the car all of a sudden becomes an entity we don't understand, and to deal with such a situation, we have specialists at the garage or workshop. Okay, I understand now why the author wants to say this because if someone were to ask me that why do embedded software engineers do not have to understand about the hardware itself? So I can now basically answer it more confidently in that way. So I can give this car's example that overall, if I were to operate and know that a certain and I had this deterministic output that it is going to do, I do not have to understand about the hardware. I'll only have to understand that if I do a certain thing, will it perform it or not? And if it is not, then definitely I do want to first thing first, something like that, right? Yes, basically I dropped off in middle. I know that's what you thought. Mm, Toggle list. The programmer's model. I think we have understood about the programmer's model already. Let me just think over that. Okay, okay, okay. Okay, so herein we are studying with the assembly language more and programmer's model. Okay, simply similar to the car, the programmer can assume the CPU to have certain parts and expect them to work a certain way. What the parts are, how they work together is called the programmer's model. Okay, what's the programmer's model? So we definitely understood about the programmer's model and what it is. Model, what's it like? Model. First thing first, what it is. The CPU to have similar to the car we can assume CPU to have certain parts and expect them to work a certain way. That's why we have our program is order. What the parts are, and how they work together is called programmer's model. Right? So the model, and just like the car, it may vary, it may vary slightly, but remains more or less the same for different types of CPUs. So the model of the CPU is a state machine. The state is maintained within bunch of registers internal to the CPU. The state is what programmer can manipulate via the sequence of instructions. The CPU can also manipulate its state as a side effect. CPU can also manipulate the state as a side effect of the computation or an external event. For the external instructions, the CPU has interrupts, addresses, data buses. So, okay, sounds like legit to me. Let's post the snippet because it's pretty much a little bit difficult to read, you know. Read. La 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 la. And then we had understanding about CPU is a state machine. We have our general purpose registers, configuration registers, CR. Okay, okay. Mm-hmm, mm-hmm. Okay. Okay, so basically, this needs more thorough reading for now. And maybe when I'm done with my own personal notes, I'll come back to you guys and let's do a quick summary about it. Same thing goes for the risk 5 thing. Yes, maybe like, yeah, that would be much better because otherwise it will take me like more time to understand. Uh, I hope you definitely understand what I'm trying to tell you over here because now I'm feeling a little bit dizzy and yeah. So before we, you know, see code, build process, this file assembler, and then we have assembler for the assembler, and then we have our REST 5 assembler. Okay. This document is very thorough, honestly speaking, and uh, it is like, okay, the C language. Now we have come to the main part of it. Hmm. It has all the parts to it, and yes. Okay. So with this, I'd love to end this live session for now. We'll come back to the CPU model thing and get over with it soon. So, if you have any queries or some sort of doubt, you can type in the comment section. That is totally open. And I don't know how come the session I try to keep it very short. So, yes, hasta la vista. See you soon. Bye, guys.